So I will give the entertainment for this lunch, and you should feel free, it's a conversation, feel free to interrupt, ask questions, or wait until the end and ask me questions then. So my talk title is Anatomy of Paradigm Shifts, which is basically the idea that sometimes we are wrong. Everyone is wrong, and in science, we should all rely on evidence. And that's why many of you are collecting observational data, because very often we have an idea or a belief about reality that is not true. And of course, if the cycle of feedback is many decades, as the case of string theory, then people can work for their entire career on an idea that is wrong. But they don't know that. So they do intellectual gymnastics, impressing each other about how smart they are. But this is not necessarily physics. I mean, it could be part of mathematics. It may not describe reality. It may be intellectually stimulating. But what we are all after as astrophysicists is understanding the universe. And that is a taller bar, because there is only one reality out of many possibilities. Unless you believe in the multiverse, but then you can never visit those other areas. I think the multiverse is actually a bad idea, because it gives an incentive to students who get a D in an exam to believe that that's not so bad, because there is a copy of them somewhere else where they get an A. So they don't take responsibility. At any event, I will try to describe the process by which we learn. So science is a learning experience. And that means being modest and allowing ourselves to be wrong. It also means that you should be open-minded. Even if there is a cherished belief, when the data tells you otherwise, you should switch to another paradigm. So let me give you an example. What would be a paradigm-changing discovery close to home? Well, the solar system has two bodies that have liquids on their surface. The first one is Earth, liquid water, life as we know it. The second one is Titan, a moon of Saturn. It has liquid methane and ethane, surface temperature about 90 degrees above absolute zero. My wish is to go to Titan and fish. If I catch any fish, I will not eat it. It may be a health hazard, but it will tell us about life as we don't know it. And it's right next door. There will be actually a mission by NASA called Dragonfly that will go there. And it's quite possible that life takes very different forms elsewhere. When you go on a date with a person on Earth, you can assume the person looks very much like the image you see in the mirror, because you share the human genome with that entity. But when you deal with something that exists on another moon, another planet, near another star, all bets are off. So this would be a paradigm shift. And it's not clear to me whether we would find first extraterrestrial life as we know it, or as we don't know it. It's unclear. But that, if it's not as we know it, if it's in a different liquid, it will be a paradigm shift. And of course, we can try laboratory experiments. If you look at the history of physics, we learned the laws of physics before we discovered them in the sky. And it's amazing that the laws of physics that we find here on Earth apply all the way throughout the universe, right? That's not to be taken for granted. When I visit the rooms of my daughters in the morning, they look chaotic. And that seems to me like the natural state of these rooms. And finding the universe so organized, so ordered, so that the laws of physics that we find on Earth apply everywhere, that's remarkable. We don't think about that often, but it is surprising to me. So let me shift from liquids to solids and talk about rocks, okay? So there were two paradigm shifts, believe it or not, regarding rocks over the past 220 years. The second one had to do with continental drift. Did you know that you could have, if you lived if you go back in time, just 5% of the age of the Earth, 5% to when Earth was 95% of its present age. It's 200 million years back when the dinosaurs were roaming around. You could have walked between America, Africa, Australia. Stuart, where are you? You flew a long distance. You wouldn't need to. You could just take a car and drive all the way here. India, Antarctica, Eurasia, China. You know this song by John Lennon, Wishing the World Will Be One? It was for the dinosaurs. There was one world. You could have walked between the continents. Now, the person who first recognized that if you look at South America, it fits very nicely into Africa. And if you bring in Australia, Antarctica, and India, they fit on the other side of Africa, and everything looks like a jigsaw puzzle. His name was Alfred Wegener. He was not a geologist. He started in astronomy, actually. His PhD was in astronomy. And then he went to meteorology. So every day or two, I post an essay on medium.com. If you're interested, you can subscribe for free. And every time it's on a different topic. I don't write unless I have something new to say, okay? So this is an essay that I wrote just a few days ago. This week, actually, on, I think it was Monday. And I looked at the history of Alfred Wegener because he was initially an astronomer and then studied the atmosphere. And then he came up with, shortly after, so he was teaching in a university and everyone liked him because he was communicating very clearly. The students liked him, the professors liked him. And then he realized, there is this jigsaw puzzle. It looks like it fits. He didn't know about other people that claimed the same before him. And he started talking about it publicly. And his future father-in-law, another meteorologist, warned him. He said, don't get into a subject matter that you are not an expert in. You are a meteorologist. You should just work on meteorology, because if you delve into a new subject, you will be scrutinized. But he didn't listen. And he gave a public lecture saying, maybe continents drifted. And of course, the geologists said it's complete nonsense. How dare you work on a subject that you're not an expert on? And that continued for 40 years. He died in 1930, but for another 20 years, the geology community ridiculed the subject. There was actually, 1944, there was an important review paper saying that's nonsense. And then in the early 50s, people started examining rocks and saw that there is a very good match between the different continents on the boundaries that he conjectured to be related. And also, plants were found to match, and fossils. And then it became clear that he was correct. He was right, and that was a huge paradigm shift. And now he is regarded as the founding father of this concept, which he could not explain, and is now being related, of course, to something that came later, plate tectonics. Basically, there are underlying plates in the crust of the Earth that move around and collide with each other, and you can see that the earthquakes are lining up with places where plates interact. And that's the way we understand it now. And continents are moving at a few centimeters per year relative to each other. And there were many instances before this supercontinent existed. There were other supercontinents on Earth, if you go back in time. Okay, so that was an example for a paradigm shift. Now, the reason I bring this up, I mean, this was the latest example, but there was one before that, which has to do with the idea that rocks can fall from the sky. When that was discussed in the 18th century, it was ridiculed because people say, we see rocks on Earth. Why should they fall from the sky? Makes no sense whatsoever. And then in 1803, there was a meteor shower that was noticed by many people in Liège, France. And there was a famous physicist, Biot. You may know him from the history of electromagnetism, the Biot-Savart law. And he went there, interviewed people, and said, it's really unlikely that there would be a conspiracy, people from completely different professions talking about the same things coming from the sky. It must be real, and they found some evidence for the rocks that looked very different than anything else on Earth. So that convinced, the fact that he was also a very good communicator convinced people that indeed rocks can fall from the sky. Another paradigm shift. What's the next paradigm shift about rocks? That's what I will talk about. So anyway, the reason I bring this up, that was on Monday. I wrote this essay on Monday, and then I realized, well, continents drift at a few centimeters per year. So does it affect anything in astronomy? So for example, the most sensitive measurements are for long baseline interferometry related. So obviously, that can be used to measure continental drift. Does it affect the pulsar timing arrays? Check the numbers on Monday afternoon. They don't seem to be significant. Then I thought, okay, but what about us? What about interstellar objects, objects that come into the solar system from outside? They jiggle the solar system. They could also affect those pulsar timing arrays. Check the numbers, not interesting. Then I thought, okay, what about primordial black holes? If they make the dark matter, there is much more mass density in primordial black holes. Check the numbers. Didn't quite work out in terms of pulsar timing arrays. And then I woke up at 2 a.m. on Tuesday, this week, just the day after, and I suddenly realized, what about the asteroid belt? Actually, orbits in that belt have a period of a few years, because it's just outside the orbit of the Earth. And that's the period related to the 1 to 10 nanohertz of the pulsar timing arrays. And then I looked into the ephemeris model that is used to pinpoint the barycenter, the center of mass of the solar system. And they include only 363 asteroids there. But there are many more. So if you just go below the modeled population of asteroids, and there is momentum conservation, that's equation number 2. So by the way, a few hours later, I wrote this paper and submitted it for publication. So woke at 10 a.m. in the morning, had my morning jog, wrote the paper, submitted it. Because it's such simple physics, you do momentum conservation of the sun. The sun is the main component of the solar system against all these unmodeled asteroids, which basically make a swarm of objects around the sun. So the situation is very similar to a black hole, and Smadar talked about it, a black hole surrounded by stars, okay? That was worked out, and in fact, we worked on it with Lars and a student, Pinaki Chatterjee, and showed that a black hole would go through a Brownian motion, just like a particle of dust embedded in air. The molecules kick it around, and that's the idea of that molecules exist came from Brownian motion. And so a black hole, a supermassive black hole at the center of a galaxy is being kicked around gravitationally by stars. and it executes Brownian motion. But then the sun, because of all these asteroids surrounding it from the asteroid belt, will execute also a random motion, Brownian. Let's check the numbers. So you just do momentum conservation. The motion of the sun reflects the motion of the objects that are not modeled around it. And then you square both sides of the equation, and you end up with a very simple formula for how much should be the root mean square velocity fluctuations of the sun as a result of the unmodeled population of rocks around the sun. And you end up with an amplitude of the signal. And it turns out that it translates, if you were to misinterpret that with a gravitational wave background, it would be just the amplitude that was reported by the pulsar timing arrays. So I put this out, and it's now on the archive. And of course, the way to tell whether the pulsar timing array measured the gravitational wave background or the motion of rocks around the sun is if they can demonstrate that indeed they have a quadrupole signal, that the correlations of pulsars are such that the timing variations are such that they show a quadrupole pattern. But that was not yet demonstrated. So anyway, this was just an example how innovative ideas can come just from one thing to another on a subject that you don't need to be an expert on. You just think about it critically, independently. Now, yesterday, as I was sitting here, you see May 9th, 11:51 a.m., I got an email from Neil deGrasse Tyson. And he saw my paper and said, that's a fun paper. So I'll just read you the email that he sent. And he said, pleased to see you are still capable of a prosaic explanation in place of an extraordinary one instead of an extraordinary explanation in place of a prosaic one. He was trying to make fun of me. And then he quoted a sentence from one of my old papers, and we will talk about that more. And the sentence says, a more exotic scenario is that Oumuamua may be a fully operational probe sent intentionally to Earth's vicinity by an alien civilization. So he said, who would believe that, okay? And he just attended a talk about solar acoustic oscillations, and maybe they introduced some signal to the pulsar timing arrays. So my reply to him was short. I said, I enjoy the challenge of going against the wind. It is fun, and you should try it sometimes. And that's the difference between science popularizers and people who practice science. It's just the same as the difference between soccer players and those that sit on the bench and criticize them, right? They tell the soccer players how to pass the ball. How dare they? And moreover, the solar oscillations have a characteristic frequency usually of 5 minutes. So if you average them over a few years, they will contribute nothing. So when I go out at night and look at the sky, I see all these lights from the Milky Way stars. And they look like lights from the cabins of a giant spaceship moving through space. And of course, the question to ask is, are there any passengers in those cabins other than us? This is an image from the Webb telescope. Now, the traditional way of answering this question for 70 years was pioneered by Frank Drake, who actually spent time here at Harvard. And that was to wait for a radio signal. But that's just like waiting for a phone call at home. Nobody may call you because they don't realize that you're lonely. Or they might be addicted to their digital screens. And obviously, radio signals propagated at the speed of light. So 1 million years ago, if they passed near Earth, they are now 1 million light years away. However, there is a better method, looking for objects, like the spacecraft that we launched 5 of them to interstellar space, and they will exit the solar system in 10,000 years. They will not be functional anymore. Voyager 1, Voyager 2, Pioneer 10, Pioneer 11, New Horizons. They will be space junk. So we are polluting interstellar space. These objects are moving at 30 kilometers per second. The escape speed from the Milky Way galaxy in the vicinity of the sun is 500 kilometers per second. So they will accumulate in the Milky Way galaxy over billions of years, just like plastics in the ocean. Have we checked our backyard? Well, it turns out that only over the past decade, we found the first objects from interstellar space. The first reported one was discovered by Pan-STARRS. It was given in Hawaii. It was given the name Oumuamua, which means a scout in the Hawaiian language. This is an artist illustration of that object made by Iso. The reason it was depicted this way is because the amount of sunlight reflected from it changed by a factor of 10 as it was tumbling every 8 hours. And so a detailed analysis of the variation of light actually indicated that it's most likely flat at a 90% confidence. There was a paper in Monthly Notices about it. So a flat object, at least 10 times longer than it is wide, doesn't resemble the rocks that we had seen in the solar system. Of course, it could be a rock that is produced by an environment very different than the solar system. We can learn something new. It also showed an excess push away from the sun without showing any cometary evaporation when the Spitzer Space Telescope looked at it. So it was not the rocket effect that was pushing it. And one possibility that I brought up in an UpJ Letters paper that Neil deGrasse Tyson quoted is that it was pushed by reflecting sunlight. Turns out that 3 years later, in September 2020, actually the Pan-STARRS telescope discovered another object that was pushed away by reflecting sunlight, no cometary evaporation. And then within a few weeks, the astronomers realized that one is actually a rocket booster from a 1966 launch by NASA to the moon. And so we know that one had thin walls, and that's why it exhibited push away from the sun. We don't know what Oumuamua was because we didn't take enough data. So the key is, in the future, to take more data of an interstellar object like it. It was the size of a football field. If it was just like a plastic bag tumbling in the wind, a very thin object pushed by sunlight, we would be able to figure it out with more data. Now, Enrico Fermi in the early 1950s was sitting for lunch at Los Alamos, and he asked, in a discussion about extraterrestrials, he asked, "Where is everybody?" Now, of course, this is a question that any single person asks. And the answer is, you can't just stay at home and ask, where is everybody? You need to leave home or look at the very least, look through the windows and check if there are any people outside, or check your backyard to see if there is any tennis ball thrown by a neighbor. And only over the past decade, we started doing that. And so I was invited by the Polish government a couple of months ago to give a keynote lecture in celebration of 550 years to the birth of Nicolaus Copernicus. So I went to the birth town of Nicolaus Copernicus. They gave me a copy of his book. And by the way, the story is really interesting. That's another paradigm shift. He was a priest. He didn't want to rock the boat. He was not controversial. And he was trying to help the church figure out when Easter is, because they used the model where the earth is at the center of the world, and they got Easter wrong by a few days. So he said, well, let me look at the data, and he realized that if you put the sun in the middle, you can predict when Easter takes place much better. So he said, here is a model. And the church said, great, we will use this model, but we will still argue that the Earth is at the center. This is just a theoretical model. And they banned his book and made it forbidden until the 19th century. And on his deathbed, he saw the first publication, print of his book. He didn't want to rock the boat, but sometimes you do have to rock the boat if it goes in the wrong direction. And that's what Galileo Galilei also realized, and he was controversial. He was put in house arrest because he actually made statements that infuriated the church. Today, he would have been canceled on social media. Now, this is a real image of the Tesla Roadster car that was launched by SpaceX on the Falcon Heavy in 2018. And they attached a camera that shows the Earth behind the car. The car is on an elliptic orbit around the sun, and there was an archive preprint that calculated that in about 20 million years, it will either collide with Earth or with the sun. Just imagine this car colliding with Earth without the astronomers anticipating it. They would argue it's a rock of a type that we've never seen before. By the way, we cannot actually see the reflected sunlight from this car at its current distance with the best telescopes we have. So I just make the point that Elon Musk is probably not the most accomplished entrepreneur, space entrepreneur, since the Big Bang. 13.8 billion years ago. There must be a lot of space trash out there, and we just need to look for it. And there is often the claim, extraordinary claims require extraordinary evidence. That was advertised by Carl Sagan. And the point is, you need evidence, not extraordinary evidence. And the second point is, extraordinary evidence requires extraordinary funding. Most people do not seek the evidence, they just have an opinion. And actually, science is progressing through hard work of collecting the evidence. And Elon Musk, for example, claims, I have all these communication satellites, haven't seen anything unusual. Well, they are not equipped with the kind of instruments that will reveal if anything unusual is in the sky. So new scientific knowledge does not fall into our lap. We had to invest $10 billion in the Large Hadron Collider to find the Higgs boson. We had to invest $10 billion in the Webb telescope to find the first generation or second generation of galaxies. It's a lot of work. And the frontier of interstellar objects, which is the third potential paradigm shift in the context of rocks, was just opened over the past decade. It turns out that there was an object before Oumuamua that the US government satellites noticed. It was a meteor, half a meter in size, the size of a watermelon, collided with Earth, and the US government has this network of satellites that are monitoring the Earth for ballistic missiles that might be launched by adversarial countries. And within a fraction of a second, they can tell if a missile was launched. And in fact, they worked around the clock recently when Iran launched a lot of missiles. So they detect also the fireball from rocks or objects colliding with Earth, meteors, and then they realize that's not of national security interest. So they post the data on a NASA website, JPL, and there is a catalog of meteors over the past decade. And there was one from January 8th, 2014, exactly a decade ago, that we looked into, and the data on the velocity indicated that the object is not bound to the sun. It's above the escape speed from the solar system, so it's an interstellar meteor. That was really the first object because it was almost 4 years before Oumuamua was reported. And then there was a comet. And the comet was discovered by Gennady Borisov, an amateur astronomer, and it looked just like the comets that we are familiar with. No surprise there. And so some astronomers asked me, well, this one looks natural because it's familiar. Doesn't it convince you that Oumuamua was also familiar or natural? And I said, well, if you go down the street and you see a weird person, and after that you see a normal person, it doesn't make the weird person normal. Now, the US government had 3 reports that were delivered by the Director of National Intelligence to the US Congress over the past 3 years, talking about objects that they cannot identify. That doesn't mean anything. There is a lot of crap in the sky, and it could be human-made, but at any event, what is remarkable about these reports is that if these objects were all human-made, the Director of National Intelligence is admitting that that the agency is not doing its job because they cannot figure out what these objects are. And so there is a project here at Harvard called the Galileo project that I'm leading, where we built an observatory looking at the sky instead of waiting for the government to figure it out. And this observatory is currently collecting data. And we had, over the past few months, about 500,000 objects that we collected data on and analyzed it with machine learning software. And so far, we haven't seen anything other than familiar objects: birds, drones, balloons, airplanes, satellites. And if we don't see anything, so be it, and it's possible the US government is not competent scientifically. They just don't figure out what all the objects are, but we definitely have the instruments to do that. And we are building a second copy of this observatory in Colorado right now, and we just got almost $600,000 to build a third copy in Pennsylvania. So there will be 3 observatories operating within a year, providing about 100,000 objects in the sky from each location per month. So it will be a huge, millions of objects, and we will get to the bottom of it. Again, evidence is the key. But what I wanted to describe quickly is an expedition. So believe it or not, late in my life, I'm trying to become more experimental, even though I focused on theory early on. And this has to do with the interstellar meteor. I decided once the US government confirmed that it is interstellar, they looked back at their data and confirmed in March 2022 that indeed the velocity implies that at the 99.999%, this object came from outside the solar system. I decided to lead an expedition to the Pacific Ocean, the location of this fireball where the meteor was spotted. And this was an expedition that cost $1.5 million. There were about 30 people on the ship. And one other thing that I wanted to mention is there were 3 flares that were reported by the US government satellites, and they were separated by 1/10 of a second. And these explosions, detonations, took place at the lower atmosphere of the Earth, indicating that the object had a very unusual material strength, tougher than iron meteorites. So the object was actually outside the solar system based on its velocity. It was moving at 60 kilometers per second, faster than 95% of all the stars in the vicinity of the sun relative to the local standard of rest. And moreover, it had material strength tougher than iron. So, what was it? Where did it come from? That was an interesting, even if it's a rock from another star, it must have been a different type of rock than we find in the solar system, because the toughest meteors are associated with iron meteorites. So this is the group of people on the ship. As you may imagine, I really wanted to have a mixed group, but we had living quarters that were very tight. And so my wife said, you need to break the symmetry, either have all women or all men, because it was very difficult, under the living conditions to have a mixed group in the same expedition. So at any event, in the next one, we'll try to get a bigger ship. So this is the group, and the ship was fittingly called Silver Star. It was from Australia, and we went there on June 14th to 28th, 2023, last year, about 9 months ago, or actually 11 months ago. And these are some photos from that expedition. So what we did is build a sled, you can see it here, which was covered by magnets on both sides. We placed it on the ocean floor, which was about 2 kilometers deep. The region that was localized by the Department of Defense was roughly 10 kilometers in size. So just think about it going back and forth with a sled, dragging it on the ocean floor, skimming the surface, and going back and forth. We did it 26 times across a region that is the size of a big city, where the ocean depth is 2 kilometers. So that was the challenge, to find something. And this is how we brought the sled from the ocean floor to the deck. And as we would bring it up, we would scrape the magnets. And we did it at night, during the day. I didn't get much sleep because people would wake me up as the chief scientist whenever it was brought up, and it would take 8 hours for every run. What you see at the bottom is a filming crew. I was jogging every morning at sunrise, as I do on land. So I decided to keep this habit on the ship. And by the way, I use a workout app that tells me how far I run. And it showed that I'm running much slower than on land. Usually 3 miles take me less than half an hour. And there I was running much slower. And only after several days, I realized it actually measures the velocity of the ship, not me. It's the GPS system. So it's not the jet lag or anything. Anyway, so one morning, the filming crew from Netflix, they are making a documentary right now. It will come out in 2025. So they were filming me, and they asked me to jog for 3 times longer. So it was actually 10 miles, about 15 kilometers that morning for an hour and a half. They even used a drone. And at the end, the director of that documentary said, Avi, it looks like you're running. Are you running away from something or towards something? And I said, both. I'm running away from some of my colleagues that have strong opinions without seeking evidence. And I'm running towards a higher intelligence in interstellar space. And so we would bring the sled down on the deck and then use even a vacuum cleaner to collect all the materials and then dry them up and put them under a microscope. And then after the 6th day, we started finding those spherules. These are molten droplets, very distinct from the background sand. We would pick them with tweezers. And this is after a rainy night. As you can see, this is our funder, Charles Hoskinson, that just arranged a Zoom call with me and said, you have the money. And he also volunteered to help. And so this is the case in which we shipped the material by FedEx. I was worried at customs that they may confiscate it. So we shipped it by FedEx, and it arrived at my doorstep, and I brought it to the laboratory of my colleague, Professor Stein Jacobson here at Harvard, who is a world-renowned geochemist. And you can see him standing next to me, much taller than I am. And on the other side is a summer intern, Sophie Bergstrom, that came. She had aspirations to become a science journalist. And so she wanted to shadow me and just see whatever I do. And at some point, she said, how can I help with the science? And I said, well, here is a pair of tweezers and a microscope, and why don't you look for more spherules? And actually, she found, on the ship, we found about 50. She found about 650. So I called her the spherules hunter. And she's coming actually in a couple of weeks to work with me on astronomy, actually on black holes now. But this is, for example, the mass spectrometer in the laboratory of Stein Jacobson. So we had altogether 850 molten droplets, these spherules, and we analyzed the composition and the shape of those. These are electron microprobe images of those spherules. We found that most of them are familiar. They are just what are called primitive spherules from meteors that come from the solar system. And they have different types, but about 10% of the spherules, about 80 of them, have a different chemical composition, and they look a little different. And we call them differentiated. And differentiated because when we look at 60 elements from the periodic table, and here they are organized based on volatility. It means the elements on the right evaporate very quickly during an explosion, whereas the elements on the left do not. And what we found is that some elements are up to 1,000 times more abundant in those spherules than in standard solar system materials. And these elements include beryllium, lanthanum, uranium. So we have this kind of a composition was never reported in the scientific literature. We had to give it a name. And so we called it BELAU, for beryllium, lanthanum, uranium. And it was consistent. Now you ask, where could it come from? Well, together with Morgan McLeod, I don't know if he's over there, we came up with a simple natural origin. The most common type of star is a dwarf star, 10% of the mass of the sun. Now, it's also 10% of the size of the sun, because radius is roughly proportional to mass for low-mass stars. And that means that dwarf stars are 100 times denser than the sun. If you take the Earth and bring it close to the sun, and I don't recommend doing that, but I'm just saying, it will not be tidally disrupted until it gets engulfed by the sun, because the density of rock is 2 times bigger than the mean density of the sun. However, if you take the Earth and bring it close to a dwarf star, the most common type of star, it will spaghettify it, create a tidal stream of rocks, half of which will be ejected to interstellar space. And guess what? The speed at which it will be ejected is 60 kilometers per second, if you do the calculation, which is just the speed of this meteor. And so when things, it's just like with the pulsar timing array. I just calculated the effect of the asteroids on the jitter of the sun, and I said, okay, these asteroids are not accounted for. I end up getting a signal of the magnitude that the PTAs were reporting. That cannot be a coincidence. The same case here. Why would a simple calculation of tidal disruption of rocky planets near the most common type of star give you the velocity that was recorded for this meteor? So this is a paper that by now was published in Astronomy and Astrophysics, where we show that tidal disruption of rocky planets could be the origin of interstellar objects, like this meteor. And the idea is that if you have another planet more massive, it will excite high eccentricity for rocky planets, and that would lead to the tidal disruption. Now, the response of some very aggressive people from the scientific community was to dismiss any aspect of this. So one immediate claim by a person who works actually on the microwave background, he published a note in RNAS saying, oh, it's just coal ash. And then reporters went to that person and made a big story. Oh, this expedition just found coal ash, which is basically very common on Earth. If you burn, wood, you end up with coal ash. Okay, so we had to check it. We went and looked at 55 elements from the periodic table, and we found that some of the elements are way different by orders of magnitude than coal ash. So it's not coal ash. And why would someone claim that it's coal ash if that someone had no access to the materials? Just shows you that people have a tendency to step on any flower that rises above the grass level. And then there was a claim more recently, which was mind-boggling as far as I'm concerned, because what they said is, okay, we don't believe the US government. The data that came from the satellites is not to be believed. which by itself is a very rude statement because the US Space Command is getting $30 billion a year, more than the budget of NASA. And if they were to make mistakes by a factor of 3 in the speed of objects that they monitor, they would report to the US president that a ballistic missile is heading towards Mexico and it's heading towards Washington, D.C. That's unheard of. How wouldn't you be worried that you're wasting your taxpayers' money if this agency doesn't know what they're talking about? And they actually went back to look at the data and reported to NASA in this official letter that they think that it's at the 99.999% interstellar. Nevertheless, these astronomers recently, just a couple of months ago, said, we don't believe the US government, forget about their data. Now let's look at other data. There are seismometers in the area. They give a much larger error ellipse. Therefore, maybe they went to the wrong place. The expedition went to the wrong place because the error ellipse is much bigger if you rely on the seismometer. And in fact, one of the seismometers was doubted as being a signal from a truck that was passing by. So then the New York Times reported the meteor is a truck. Now, if they report so superficially about scientific matters, I wonder whether you can believe anything they say about politics. We were guided by US government satellite data. That's what dictated the error box that we went to. We looked at some seismometer data, decided that it's not reliable. Obviously, one seismometer can only give you a circle based on the time delay between the sound signal compared to the light. And it can only give you a circle. It can't localize anything. And nevertheless, this New York Times report was saying you went to the wrong place because the seismometer is not to be believed, which is a complete distortion of the story. So anyway, we went 26 times based on this red region, which was defined by the US Department of Defense. And so we found those spherules, but they don't tell us specifically the nature of the object, so we want to find bigger pieces. And once again, evidence is the key. So what you see here is from the last day of the expedition. Next to me is Art Wright, who was, he's 85 years old. Always reminds me of my father because he doesn't say much, but everything he says is true. And that's a quality that you appreciate. I mean, some people as they age become, like that. And so he was actually the party chief. He was managing the expedition, the navigation. And here we were looking at the sunset on the last day, planning the next expedition to look for bigger pieces. And we now have a clear plan. It will cost $6.5 million. And at this point, we are just waiting for a potential funder. There's a number of potentially interested people. And we hope to have it in summer 2025, a year from now. It will be a much longer expedition, about a month. And it will involve a remotely operated vehicle where we would basically we will have a video feed of where we are on the ocean floor. We didn't have that with the sled. And we would see what we are picking up. And we would try to pick big pieces. If, for example, the core of the object survived the wreckage, then we would know what it was, and we can easily tell if it's the model that Morgan and I came up with, because one can examine the composition of this rock in that case. Now, there is another path forward, and we will hear more about it from Mario this afternoon. It's the Rubin observatory in Chile that will start operations in 2025. So we don't need to wait a long time. All I'm saying is progress can be made within a year on both fronts. And in the context of LSST, this is the camera of LSST that is the size of a person. It's quite amazing. It looks like a regular camera. It has already 3.2 billion pixels, 1,000 times more pixels than you have in your cell phone. And it will survey the southern sky every 4 days. So simple calculation shows that it should detect an object like Oumuamua every month or a few months. And with one of my postdocs, we developed the pipeline, the software that would allow us to search for those objects and alert other observatories to look for them, because we need this alert system early enough to get much more data. 2 meters or so. What is the exact size of the aperture, Mario? It's about 2 meters. No? What's the size of the 1. The diameter or the radius? Diameter. 1.2 meters? Because I saw people standing next to it and they're shorter than this. No? Okay, so it's, okay, 1.2 meters. Okay. Well, when we find more of the object, a population of objects that look as weird as Oumuamua was, we will probably figure out what it was, whether it was space trash, whether it was rocks from another type of star, or something else. So that's all I wanted to mention. That's the third potential paradigm shift that we might have with respect to rocks. And what I wanted you to take away from all of this is that it's really, even though it sounds straightforward that science should be based on evidence and any observer recognizes that, it's not as simple when you deal with evidence that doesn't conform to what people believe in. And some of the experts, quote unquote, resist change in their traditional thinking. And the challenge is to convince them to collect data, because they would prefer. I once asked my research team, I said, what would make a theorist happy? And since we have a lot of theorists here, I challenge you as well. What would make a theorist happy? Lack of data. Because then you have no chance of being proven wrong. And obviously, string theory is an excellent opportunity for that, right? Because you can demonstrate that you're smart, do intellectual gymnastics for decades and get prizes, awards, recognition, and continue to argue that you might be describing reality even though you have no evidence whatsoever. And just to close, I will mention an anecdote. About a year ago, I went to a breakfast with a string theorist, and it's one of the prominent ones. I will not mention the name. And I said, what is the most important paper that you wrote in your career? He's like in his late 60s. And he said, it's a paper about supersymmetry. I said, well, but the Large Hadron Collider was searching for supersymmetry in the natural parameter space, didn't find it. Doesn't it make you concerned? Why would you be proud of a paper that predicted something that was not found? I mean, coming from a culture of evidence-based science, sounds to me like a no-go, right? So he said, well, who knows? If we just go to higher energies, maybe we'll find supersymmetry. And it reminded me of the Jewish Orthodox community in Crown Heights, Brooklyn. They had a theoretical model that their rabbi will become the Messiah after he dies. And then there was a data point. He died, okay? And he never came back. What did they say? So you might think, like any scientist, they would say, okay, our model was wrong. No, like any scientist, they said, we just have to wait. He will come. So then I ask you, is there a difference between religious beliefs and scientific beliefs? If you always say something will happen if we just wait long enough, and you keep insisting that an animal that doesn't have stripes is a zebra, then isn't that an emotional belief that has nothing to do with seeking evidence? And that's the thing that we should resist the most when doing science. And unfortunately, very often the mainstream has that approach. So I just wanted to communicate that based on all the bruises that I got over the past few years. and I'll be glad to discuss if you have any questions. Thank you. Smadar?
What's the sky coverage of the Galileo satellite? And were you able to find, for example, there was a balloon that came from China, where the Galileo satellite, not the satellite project, are able to capture it?
Right. Yeah, so interestingly, the spy balloon from China was spotted by satellites. And in fact, Eric Kito, sitting here, wrote a paper because we got access to Planet Lab data. That's publicly available data from satellites that are commercial. And you can trace the balloon going from China all the way to the US. The question of whether it was intentional or not is a separate matter, but you can actually see it. And that's the paper that you can ask Eric for more details. But our observatories can only see out to a distance of a few kilometers from the observatory site because of the atmosphere. And unless we are looking at we did see some satellites actually, but those are way up. But in terms of the horizon, we can only see a few kilometers away. And so far, we've seen mostly birds and airplanes.
And I want to comment that at the end, because you seek the data, so even though people, I don't know, that the dude with a coal or whatever, but you went and proved them wrong. So kudos to you.
Thank you. But it's what I wanted to say is that there is a very large asymmetry between putting a lot of, it took us a year to plan the expedition, a lot of Zoom calls. Then going there for a few weeks, was exhausting because I didn't sleep much. I wrote 43 diary reports that were read by millions of people around the world. They were translated to Spanish. The public was extremely excited about seeing how science is done by collecting evidence. And then those critics, a few, not many, they don't do much work. Like they sit on their chair and just raise dust and claim that they can't see anything. So the work of a critic is to raise enough dust so that you can't see anything. And that is much easier because you can do that for any scientific endeavor, any work that is being done in the maze. Like, why is this dust not being raised in the context of string theory, I ask? Couldn't you doubt that much more than rocks? And it's just because this is accepted or it's not part of their territory and they don't feel that they are threatened about their traditional beliefs about solar system rocks. But it's completely natural that there would be rocks coming from outside the solar system. So why resist that? I just don't understand that approach. And actually, in the paper that we wrote with Morgan, which was just bread and butter of astronomy, like nothing really speculative about the process that we considered, even there, some of the referees came from that community of critics that didn't really understand how tidal disruption operates. And they made real mistakes in criticizing. But then others understood it immediately. And anyway.
So you're going to have, with LSST, Rubin, you're going to have lots of Oumuamua-like objects.
Right.
And, with Oumuamua, it was, by the time we had found it and understood it was important, it was already gone.
Right.
So what's the plan now, thinking ahead to the data?
Right.
With the follow-up of
Right.
Oumuamua-like.
So first thing is we want to catch it early enough so that it's approaching Earth. Now, in principle, if you ask me if I had a very large budget, let's say $1 billion or more, I would design a space mission of probe that is waiting for LSST alerts that would meet the incoming object along its path. For that, you need to just maneuver the probe at about 10 kilometers per second. You can't do it with 2 kilometers per second. There is a European mission, but it's really not moving fast enough to meet the object in time. You need something of order 10 kilometers per second because these objects are coming at more than typically 40 kilometers per second. So you need to go to the right place so that you meet them along their path. And then you need to come close to them. So we worked out the numbers, and you need to equip them with a big enough aperture to be able to. But even if you don't do that, which is billions of dollars in cost, from Earth, you want to employ a lot of telescopes collecting data. And that kind of a set of observations was not done to the fullest with Oumuamua. We just got because everyone assumed it's just a rock, asteroid. And so for the next one, we want to really get everything we can about it. And so with an early enough alert, we can use the best telescopes on Earth and get a lot of data. Now, the other thing with the Webb telescope, if we can look at it, if it's not towards the sun, then the Webb telescope can give us amazing information because, first of all, you will see it from a different direction than the Earth-based telescopes, right? Because it's 1.5 million kilometers away from Earth and looking at the same, so you have a parallax. And you can pinpoint the three-dimensional trajectory extremely accurately and measure any excess acceleration that is non-gravitational very precisely. And moreover, you detect the infrared emission from the object. So the surface temperature of an object is dictated by its distance from the sun. As long as the albedo is small, the energy that comes from the sun on the surface is re-emitted, right? So there is energy balance between absorption and emission. And you can tell the surface temperature from that. Sigma T to the fourth is per unit area, and then you know how much. So you figure out the temperature. Now, if the Webb telescope measures the temperature from the infrared, because 300 degrees Kelvin at the Earth's orbit is in the infrared, okay? And so you can tell the temperature, you can tell the distance, and you can tell the flux. So if you know the 3D position, you can actually say how big the object is. And you can infer the albedo because you see also the reflected sunlight from it. So altogether, you can pinpoint, you can figure out the size of the object, temperature, non-gravitational acceleration by having the Webb telescope look at it. And that's something we didn't have with Oumuamua. So that would be amazing. And hopefully, it will not move in the direction of the sun at that. So I think Webb telescope observations, anyone that has access to the Webb, and if there will be an interstellar object from LSST next year, get time on the Webb and look at it. That would be amazing. Yeah. Yeah. Sorry. Okay, when is the next? Oh, it should start at 1:30? Okay. Okay, go ahead.
Well, when you asked what would make a theorist really happy, and before you said anything, I thought to myself, I said, well, really good data. Because two things can happen, depending on when you get the data. So either you have the data before you start working on the theories, and then I say, oh, this is great, because now I already know the answer. I just have to work it out. And then if you don't have the data, it comes later. And then you say, well, this is really great, because now at least I'm going to learn something. So,
right.
So I said, well, either you didn't get it right, and then you can fix it.
You can revise it, yeah.
Say, hooray, I made it pretty good.
Well, just to give you an example, we wrote with Steve Forlanetto, my former student, we wrote a book about the first galaxies in the universe. And people asked me, what do I hope the Webb telescope might find? And I said, something that we didn't expect. And indeed, it found those things. And because then you learn something new. It's much more rewarding to learn. I mean, it's very boring, even though it's good for your ego as a theorist, to predict everything that is being observed. And that's what we strive for. It's actually more exciting if it doesn't agree with what you expected, because then you learn something new. And I feel as long as you don't put your ego as the most important thing, doing science is a humbling experience, and it's really a lot of fun as long as you're not trying to show off. That's the point.
Well, I'm usually pretty happy when I'm right. So.
Oh, okay. Any other quick question? Yeah?
Okay, a question about random motion of the sun.
Yes.
There's a similar signal can be produced by small scale Earth-size dark matter
By Earth?
by Earth-size dark matter substructures.
Yeah, so that's what I looked at first. I was thinking about, these are the things that didn't really work. So I went through those, and one of them was not dark matter, but not cold dark matter, but the primordial black holes are the best. I mean, you can pick any mass you want, and they are the most compact you can imagine, so better than the clumps of cold dark matter, right? And you just assume the dark matter is made of asteroid mass primordial black holes. And you ask, okay, that will jitter the barycenter of the solar system, because these objects are coming from the halo with 300 kilometers per second. They're not bound to the sun, so they're not included in the ephemeris. We can't see them, it's dark matter, and they come and rock the solar system. That's the first thing I checked. And it turns out the numbers just don't. So I told my daughter, I said, oh, maybe I'll figure out what the dark matter is. And then I checked the numbers, and she said, Dad, do you know what the dark matter is? And I said, no, it just doesn't work out, unfortunately, you know. And that's the way, you know, you just check the numbers. But then I checked the asteroids, and it fit like a glove. So why would the asteroids that are not counted in the standard model ephemeris of the solar system, those asteroids, the thousands of them that are not counted, why would they give you just roughly the signal that was reported by the pulsar timing arrays? Now, I realized that if I write this paper, and I realized, you know, within a few hours, that I write this paper, I'll get many more enemies because, you know, this is an international team of people working on this for decades. And I just point this out, but, you know, I don't care of a little more bruises, you know. I mean, they cannot avoid the science, right? So I put it out, and I immediately wrote to Maura McLaughlin, who is the co-director of Nanograph, the Physics Frontier Center, and I also wrote to Scott Ransom. So I said, look, this is what I find, you know, you can't avoid that. And they replied that even though they don't have a proof as of yet, that within a year they hope to get evidence for the quadrupole nature. What you do is you correlate, there is this correlation of pulsars, and if it comes from a gravitational wave, there should be a quadrupole pattern to the variations in the timing of pulsars across the sky. Whereas if it's Doppler motion, you get a dipole, right? Cosine theta dependence relative to the direction of motion. So they said, we can definitely rule out a dipole, but we don't know yet for sure if it's a quadrupole. Well, my point is that the dipole is actually randomly walking in 3 dimensions. It's a vector that, because of the kicks, it's a Brownian motion, right? And so you might be misguided if you think there is a stochastic background of quadrupole kind of pattern. It's stochastic, it's also varying on the characteristic frequency. And instead, if you have a dipole that is randomly walking, maybe, you know, it would look as if maybe it's not a dipole, you know, because... So telling the difference between a random walk of a dipole and a random walk of a quadrupole is non-trivial. They were thinking about something that shows a clear, like if you have just a plain wave, gravitational wave, obviously you can tell. But for a random walk, it's not so obvious. So they agree with me, and they were not very hostile, at least in the messages.
So thank you, Avi.
Thank you.
I think we should plan to take a 5-minute break before, but unfortunately I have some other, I want to make an announcement beforehand. So as some of you will have seen in your email, but probably not all, I'm sorry to pass along the news that Jim Simons died earlier today. Jim, of course, was a major figure for a lot of us. I know that there's some folks here who are at the Simons at the CCA, so somebody who I'm sure you interacted with a lot. I've interacted with them in the context of my Simons Foundation funding, but I think for many of us in theoretical astrophysics, you know, visits to the CCA and visits to the Simons Foundation have been a real staple over the past 5 to 10 years. So I think it really is appropriate that we give Jim a moment of silence. Thank you. Life very well lived, but okay. So let's take a 5-minute break and come back after that.